Meet the atom, our universe's tiniest Lego brick. It's the smallest unit of matter that retains the properties of an element. Imagine the smallest possible piece of any element. It's so tiny, you can't see it with the naked eye. Like a single grain of gold or a speck of oxygen, these are made up of countless atoms. This tiny piece is an atom, the fundamental building block of everything around us. Inside this atom, it's a whole mini-universe with even smaller parts, each playing a crucial role. We call these subatomic particles protons, neutrons, and electrons. They are the building blocks of the atom. Protons hang out in the center, called the nucleus, with a positive charge. They help define the element. Neutrons, also in the nucleus, are neutral with no charge. They add mass and stability to the atom. Electrons are super tiny, negatively charged, and zip around the nucleus at incredible speeds. Together, these particles make the atom what it is, each contributing to its unique properties. The number of protons defines the element. For example, hydrogen has 1 proton, while gold has 79. Everything in the cosmos, from the smallest grain of sand to the largest star, is made of atoms. Think of protons, neutrons, and electrons as the atom's crew, each with a specific role. Each has a special job to do, ensuring the atom functions correctly. Like tiny planets around a star, electrons orbit the nucleus, creating a dynamic and balanced system. How did we figure all this out? How did we unravel the mysteries of the atom, the building block of everything around us? It was a journey of discovery, a quest that spanned centuries and involved countless brilliant minds. John Dalton in the early 1800s proposed that atoms were tiny, solid balls, indivisible and fundamental. J.J. Thomson in 1897 discovered the electron, revealing that atoms had smaller, negatively charged parts. Thomson imagined a plum pudding model with electrons scattered within a positively charged blob, a revolutionary idea at the time. Ernest Rutherford in 1911 conducted his famous gold foil experiment, discovering that the atom was mostly empty space with a dense, positively charged nucleus at its center. Niels Bohr in 1913 refined Rutherford's model, suggesting that electrons orbit the nucleus in specific paths or shells, much like planets orbit the sun. Each shell had a certain energy level, explaining how atoms interact with light and other forms of energy. This model helped explain atomic behavior and laid the groundwork for modern chemistry and physics. Many brilliant minds contributed to our understanding, each building on the discoveries of those who came before. From Dalton's solid balls to Bohr's orbits, each step was revolutionary and brought us closer to the truth. The journey of discovery continues, as scientists today build on this legacy, exploring the atom's deeper secrets. Science is a collaborative effort, a tapestry woven from the threads of countless contributions. Each discovery builds on the last, creating a rich history of scientific progress. The atom's story is a testament to human curiosity, ingenuity, and the relentless pursuit of knowledge. And the quest for knowledge continues, driving us ever forward into the unknown. How do we count these tiny particles? It's a question that has fascinated scientists for centuries. We use the atomic number, symbol Z, to identify and count them. The atomic number tells you the number of protons in an atom's nucleus. This is crucial information. This number is unique for each element, making it like an ID card for atoms. For instance, hydrogen has 1 proton, so Z equals 1. It's the simplest element. Helium, on the other hand, has 2 protons, so Z equals 2. It's the second simplest. Atoms like to be electrically neutral, meaning the number of electrons equals the number of protons. This balance is key. For mass, we look at the mass number, symbol A. This gives us more detailed information. The mass number is the sum of protons and neutrons in the nucleus. Electrons are super light, almost no mass, so they don't contribute much to the atom's weight. Therefore, most of an atom's mass comes from its nucleus. Finding the number of neutrons is easy. Just subtract Z from A. For example, carbon often has a mass number of 12 and an atomic number of 6. So, it has 6 neutrons. This simple calculation helps us understand the atom better. Simple math, yet it unlocks powerful cosmic knowledge about the universe. The atomic number and mass number are key to understanding the fundamental nature of elements. Electrons live in specific energy levels, or shells, around the nucleus. The shell closest to the nucleus is lowest in energy. Electrons fill these shells from inside out. Each shell can only hold a certain number of electrons. The first shell holds a maximum of 2 electrons. The second shell can hold up to 8 electrons. The third shell can also hold 8 electrons for the first 20 elements. This arrangement dictates chemistry. Hydrogen has 1 electron in shell 1. Helium has 2 electrons, filling shell 1. Lithium has 3 electrons, 2 in the first shell, 1 in the second. Neon is 2, 8. Sodium is 2, 8, 1. Calcium is 2, 8, 8, 2. Beyond element 20, things get more complex with subshells named S, P, D, and F. Isotopes are atoms of the same element with different numbers of neutrons. They have the same number of protons, so their atomic number, Z, is identical. But different neutrons mean different mass numbers, A. For example, most carbon atoms are carbon-12 with 6 protons and 6 neutrons. Some carbon atoms are carbon-14 with 6 protons and 8 neutrons. Chlorine-35 has 17 protons and 18 neutrons. Chlorine-37 has 17 protons and 20 neutrons. Isotopes have different weights but are chemically the same. Understanding atomic structure is key to chemistry. It explains how elements combine to form molecules. It helps us understand nuclear reactions in stars. It's crucial for medicine, like in imaging, and for creating new materials. From the smallest scales, the grandest truths emerge. The atom is a universe in itself.